the stochastic analysis of the NT. So just want to highlight that some things are presented also with Isaac Gonzalez, who is a PhD student of Andreas's as well. So there's some results that we've done together in this as well. Otherwise, it's the same people. So we've looked in the last hour quite a bit at the average behavior of the branching process, how this is related to the neutron transport equation, and how we can use the branching process and the probabilistic perspective to try to come up with new simulation techniques, so based on the many to one, the biasing, and so on. And as I said before, I think Alex and Minwon will talk more about that in their talks. So for this part, I want to focus a little bit more, well, to go more in depth on the long-term behavior of the system. So looking at the stochastic behavior as well as the average behavior. So not just saying if I simulate lots of processes and what's the average that these repeats tell me, but if I just simulate one process, what can I learn from the long-term behavior of this one system and the fluctuations of the system? And so there are two main tools that I will use to talk about this. The first is the martingale that we didn't talk about before, so I'll redefine it shortly. So the martingale behavior of the other martingale that we didn't look at, and the Powell-Bell equation, which is the non-linear version of the neutron transport equation. And then we can use these two tools to try to look at the sort of long-term stochastic and average behavior of the system in more depth in each of the critical, supercritical, and subcritical cases. And then I'm going to finish on another eigenvalue problem, which then invokes another neutron branching process in subsets. So we said that because of the right eigenfunction, we can define this martingale. And this is a non-negative martingale, and so it has an almost sure limit, which I'll denote W infinity. And we can characterize the behavior of the system in some sense based on what happens to W infinity in the different regimes of critical, subcritical, and supercritical. So the first thing I'll do is introduce another assumption, which is there exists some open ball that's compactly embedded in the spatial domain in the reactor, such that if I look at the fission activity on this ball and then anywhere in the velocity domain, it's infimum is strictly positive. And this just ensures that there's somewhere in the reactor where you're guaranteed to have a minimal fission activity. And under the assumptions, so all of the assumptions that I've defined up until now, we can characterize the system as follows. So if lambda star is negative or equal to 0, so if I'm subcritical or critical, then the martingale limit is equal to 0. And if it's positive, then it's L2 convergent. And it doesn't matter what the sign of lambda star is, we can show that the event that the martingale limit is 0 is equal to almost surely to the event of extinction of the process. And so what this is saying is that in the critical or the subcritical case, my process will die out almost surely. If I look, t to infinity into the future. And in the critical, the supercritical case, then I will have a positive probability of survival. But what happens in reality is that in the critical case, for example, you don't ever see this behavior because there are different mechanisms. For example, that when the system may be starting to die out, there's a mechanism in place that increases the fission activity, or when the fission activity is getting too high, it brings it back down again. So in the critical case, you don't ever see this extinction. And so we need to look a little bit more at what goes on when you have a critical system, but you keep it alive. And in order to do this, I'll look at my second tool, which is the Bell equation, and as I said, the nonlinear version of the neutron transport equation. So I'm going to define Pn to denote the probability that a neutron with initial configuration R and V at some time T0 will give exactly n neutrons in some subspace of my domain at some later time Tf. And then based on this, I'll define the probability generating function associated with these probabilities. And by looking at the derivative of this function and doing a similar thing to the linear neutron transport equation, so going back to sort of the physics and engineering perspective, at looking at a balance of mass, a loss and gain of neutrons, I can derive the nonlinear equation. And so this equation was given by Pell and Bell back in the 50s or 60s. And you can see that the first three terms are exactly the same. But when I come to the fission term, because I no longer have a linear object, I end up having to put down a power of the number of neutrons that I put down. So I have a fission at rate sigma f, and then I have between 1 and m neutrons, let's say, that I could possibly produce, and with probability C, I, R of V, I'll produce I neutrons, and so I put down I copies of the original process of the G, but integrated over V prime to give their new velocities. And so this is the sort of physicist slash sort of L2 version of the nonlinear equation. And so we want to go back and do exactly the same thing as with the linear equation and frame it in terms of a mild equation in order to use semigroups and the branching process. So what this means is that instead of looking at the sum of the number of particles, I'll now look at the product of the number of particles under the action of some function f. And again, same thing, I'll just look at the average of the system started from an initial particle with configuration RV. And then instead of the operator f that I had before for the fission, which was a linear object, I'll have the nonlinear branching mechanism, which again, instead of the sum, is just the product of the number of particles. So to go back to Andy's question, it's this that really does uniquely give the branching process, the nonlinear thing that really does uniquely define it, as opposed to the linear case. And so then we can write down the same thing as before. We can look at all the possible things that could happen to my particle if I start at configuration RB. So I could have moved in a straight line, or I've had some scattering or fission event, and instead of the operator f, I now have the nonlinear branching mechanism. And if you like, I can write this in terms of the semigroups U that Andreas talked about before. S plus G. And you'll notice a slight difference here in the fact that rather than having an indicator that T is before the killing time of the process, we've got the minimum of T and the killing time in here. And that's because with the nonlinear equation, we need to specify that the functions are 1 on the symmetry state on the boundary of the domain as opposed to 0. And so we have just this slight difference here, which is this U hat as opposed to U. But otherwise, it's the same kind of thing. And I just have the nonlinear term. And it turns out to be quite convenient to look at another form of the nonlinear equation. So I'm going to define a new branching operator, which is this, this function here. And it's kind of a linearization of the nonlinear branching mechanism. And the reason that I've introduced this is because I want to try to somehow linearize the nonlinear semigroup and write down an equation for this. So if I look at Vt, which is 1 minus Ut, then we can show that it satisfies this equation. And so you can see there's a link here between the nonlinear equation and the linear equation, and using this operator H instead of G. And why is it useful to look at either this equation or this equation? Well, if I was to go back to the original probability generating function, let's say, I can differentiate this this quantity and set Z equal to 1 and get information about the moments of the process. Or I can differentiate and set Z equal to 0 and get information about the probability distribution of the number of particles alive at later times. And so this is exactly what I want to do, but now with a version of the equation. And this second version is particularly useful because if I set G to be equal to 0, which I'll show in a bit more detail later, but if G is equal to 0, then Vt of 0 is the probability of survival. And so I can try to look at the long-term behavior of the probability of survival as well as the moment and the probability distribution of the number of particles. And so, as I said, one of the particularly interesting cases is the critical case, because even though we've shown that the process will die out almost surely, in practice, we never see this. There's always some way of keeping the process alive in reality. So we're going to look at what would happen if we conditioned the critical neutron branching process on survival. So I'm first going to introduce the final assumption. I promise it's the final one. And I introduce this type of variance function. And so this just kind of looks at somehow the correlation between two particles when I look at the branch, when I have the two particles applied to the branching, what's it called? What do I want to say? The offspring, that's the one. And I'm going to ask that this equality or inequality is satisfied with this function V. And what this is a kind of uniform ellipticity condition. So it ensures that the process can explore the space enough to try to keep it alive in some sense. And so on the right-hand side, we have, if I take G equal to B UT, which is if I take G to be the probability of survival, for example, this is saying, if I take two independent particles and randomize their velocities according to the stationary distribution, then my process should have a better chance of survival than if I start in this configuration from two independent particles. Okay, so it's kind of ensuring that my process spreads out enough and has a decent chance of survival. So then we have this this Jaglom theorem that looks at the critical process. So I assume that lambda star is equal to 0, and I assume all of the assumptions that I've imposed already. And if I look at the process conditioned on survival with this divided by t term, then we can show that this conditioned law is asymptotically equivalent to an exponential distribution with a parameter that I can explicitly state in terms of in terms of the process. So all of these quantities are known. They involve phi tilde, sigma f, and so on. And this is the only proof that I'm going to show because it actually offers two other results that are very, very interesting from a point of view of branching processes in general, but from a point of view of the neutron transport equation. And the plan for the proof is to show that the moments of the condition distribution converge to the moments of an exponential distribution. So if I look at these moments, condition on survival, they converge to k factorial times a kth power of this parameter. And one thing to note is that if I was to look at these moments conditioned on survival, I can write these in terms of the moments of the unconditioned process and the survival probability. So in order to get the asymptotics for this guy, I can look at the asymptotics for these moments and the asymptotic for the survival probability. So they're going to be the two main steps that will form the proof. So first of all, as I said, we're going to study the moments of the neutron branching process. So I recall the V was 1 minus UT, 1 minus the nonlinear semigroup. And suppose I take a function f, my test function f to be of the form e to the minus theta g, where theta is some positive real number and g is a bounded function. Then if I plug this in, I have 1 minus e to the minus theta of the inner product of g against the neutron branching process. And as I said, when I was looking at the probability generating function, we could differentiate this, set z equal to 1 and get the moments. And so I'm going to do the equivalent here. I'm going to differentiate Vt applied to this test function, k times, set theta equal to 0, and then out pops the kth moment of the branching process. Okay. So what would happen if we did exactly the same thing, differentiated and set theta equal to 0 to the evolution equation that Vt satisfies? So with Isaac and Andreas, we did exactly this. And we obtained this lovely looking equation here for the kth moment of the branching process. So again, you can see on the right-hand side, either my particle hasn't split and I've just got one particle, so f to the power k, or in between time 0 and t, I have branched. And when I do, I have an operator that tells me how I split my moments across the particles in some sense. It tells me how to share the moments out so that I've still got k moments, but they've split according to this branching operator. And one thing to note is that this branching operator n k minus 1 is over this sum of tuples. So it's all the tuples that sum to k, because I want to keep k moments on the left-hand side, such that at least 2 of them are strictly positive. So that means I can't have a term where I've got exactly k moments still on the right-hand side. I've always got to split into at least 2. And that means that all of the orders here that I see here, the kj's, have to be strictly less than k. And so I've got an equation where I can write the kth moment of the process in terms of all the lower order moments. Okay. And so this is going to become very useful to try to look at the asymptotics for this, because I can then start to think about an inductive argument. And so this is what we did again. So with Isaac and Andreas, we started by looking at what happened to the first moment. And we already knew what happened to this because of the Perrin-Frobenius behavior. We already know that the right normalization is 1 over phi because lambda star is equal to 0. And we know that this converges to f against phi tilde, which is exactly what we see here when we plug in L equal to 0. So then we looked at the second moment. I said, well, okay, I can use this equation and write the second moment in terms of the first moments, and use then the parent Frobenius on each of the first moments that appears here, and so on. And so we can have an inductive argument that tells us exactly the right normalization to have for the nth moment, and we can characterize precisely its limit. And the proof of this actually doesn't depend, it's not specifically for the branching process, the neutron branching process. We took a very general branching Markov process with very general motion and non-local branching. And so we can show that this result holds for a very, very large class of branching processes. And also Isaac showed that this was also true for super processes as well. But from the perspective of the neutron branching process, this could possibly start to tell us about the fluctuations of the process, because we can completely characterize the normalization required for the moments and its limit. I also want to mention as well, from the purpose of branching processes, this equation offers an idea of a many to few formula. It's not exactly as fully general as it could be, but it is a kind of many to few formula. So that was the first step, to fully characterize the moments of the branching process. For the second step, as I said, we want to then look at the convergence of the survival probability. And it turns out here that the right normalization is T, or equivalently that the probability of survival goes like a constant over T. And I won't do as many details of this part of the proof because it's a bit more involved. But as I said before, if we set the test function to be 0 and look at VT, which is 1 minus the nonlinear semigroup, and I plug in the test function 0, this quantity is 0 if NT is positive, sorry, but it's equal to 1 if NT is equal to 0. And so this is exactly, VT of 0 is exactly the survival probability. And so it's a solution to the nonlinear equation satisfied by V. And what we do is study the nonlinear equation to get, of course, upper and lower bounds of the form constant over T, and then we bootstrap these to get exactly the constant that we need in terms of the constant that's written here. Okay. And then putting these things together for the final step, as I said, I want to look at the kth moment of the conditioned process with this normalization of 1 over T to the K. I can rewrite this in terms of the kth moment of the non-conditioned process and the survival probability. I share the powers of T out to give each of the numerator and the denominator the correct normalization, and then I invoke the results that we had before. And so we obtain exactly the moments of the exponential distribution. So from this, for the critical case, we now know the asymptotic distribution for the conditioned process when it's critical. We can also explicitly characterize the limiting behavior of all of the moments. And we know the asymptotics for the survival probability as well. And now I'm going to move on to the supercritical case. So we looked at this because classically for branching processes in the supercritical case, you can obtain a strong law of large numbers. But then we wondered whether this was very useful, because if you have a supercritical neutron branching process, this might mean that your reactor is going to blow up at some point. But I've been assured that this is not always the case, that there's some regime of supercriticality that's still okay. And as I said before, there's also mechanisms in place to help reduce the number of neutrons as well. So we know from the parent Frobenius result that if we look at the average of the process and normalized by the growth term, and we converge to a stationary distribution. And what we want to ask is, if we remove this expectation here and just look at the stochastic behavior of the process, but with the same normalization, what do we get in the limit? Can we characterize this limit? Do we get something sensible? And again, it turns out that if we go back to the martingale that I introduced right at the start, that this is exactly what provides the answer, and the limit that provides this answer. So with Simon and Andreas, under some of the assumptions that I've introduced, we've shown that for a fairly large class of test functions, we get a strong law of large numbers result. And so they said, if I don't have the average there, like in the Perrin-Frobenius behavior, and I do normalize by the same thing, then I converge to the thing that appeared in the limit for the Perrin-Frobenius, but with the extra martingale limit here to account for the randomness, to account for the fact that I've removed the average behavior. And we obtain this result. This convergence is almost sure and in L2. So I won't go through the proof for this because it's quite involved. But again, we obtain this result for a very large class of branching processes. The proof holds for, again, a very general non-local branching process with a general Markov movement. And similarly with Isaac and Andreas, once we'd done the critical moments, we asked ourselves if it was possible to do the same thing for the supercritical case, but now with a different normalization. And it turns out that we could. So in the supercritical case, what we find is that the correct normalization here is e to the minus lambda t, but to the power L, so that to the same power of the as the moment we're looking at. So you need to, because this is growing exponentially fast, you need to compensate for the alpha moment here as well, and then we can characterize exactly the limit. In this case, the limit is a bit less nice. I've included it here just for completeness, but it's a bit ugly. And it's characterized exactly, it's defined inductively. And what this means is, if we were to go back to the strong law of large numbers, and we were to able to obtain this convergence in LP, for example, for p greater than 2, then this result would say, well, I also know the moments of the limit. I know the moments of the martingale limit, which is very nice. And then finally, I will move on to the subcritical case. And again, Isaac, Andreas, and myself asked the same question: can we characterize the limit of the moments in the subcritical case? And in this case, what is the correct normalization to take? And it turns out to be e to the minus lambda t. So there is no L here. And that's because we know that when lambda is negative, the growth term e to the lambda t is less than 1. And so your higher powers are decaying much faster than the first power. So it's really the first moment that needs compensating. And then all the others are fine. They're decaying quickly enough, even with this compensation. And we saw that if we tried to compensate by anything higher, then we didn't get the convergence. It wasn't the correct normalization to take. And so I realized that a lot of this is quite heavy theoretical results. It's quite general. And the next step is, what can we do with these results? Can we use the moment results? Can we use the strong law of large numbers to try to say something interesting from the point of the neutron transport equation? Can we offer anything for the simulations based on these results? And so one possible direction of research is to use the many to few type formula that we saw in the analysis of the critical moments, and a more general form to look at the genealogical structure of the process and try to say something about temporal correlations, most recent common ancestors, and so on about the process. And this is something that with Andreas Simon and Ellen Pearl that we started looking at to try to characterize this genealogy. There's also a phenomenon that appears in simulations and in branching processes in general, and it's this phenomenon of clustering that you can see by this image here. And so as you simulate the process as the branching process evolves, you start to get clusters of particles. And we want to try to understand the spatial form of these clusters, when they happen, why they happen, and how to detect when they're happening in simulations. And this turns out to be quite closely related to the moments of the process. And so this is one possible application of the moments results that we've obtained in all of the cases for criticality. As well, we haven't started looking at central limit theorems. And again, this is related to the moments of the process, and also laws of large numbers in terms of initial population size. And finally, can we obtain precise rates for the rates of convergence of all of these results to try to obtain Monte Carlo error bounds for simulations? Okay. And the last part I want to move on to is the neutron generational process. So I'm introducing this because I think about halfway through my PhD, we were visiting the answers team, and we said we've got all these great results. We've got the strong law of large numbers, we've got the Perrin-Frobenius results, you know, we've got all of these really nice results. And they said, oh, actually, it's a different eigenvalue problem that we're interested in, or that this eigenvalue problem is still interesting, but there is another one that is used more often. So I'm going to present this second eigenvalue problem and how this changes the probabilistic perspective. And I think this is something that Alex will focus on more tomorrow as well. So the other eigenvalue problem is called the k-effective problem. And this is again to find a triple, so a real number kf and a functions phi and phi tilde, such that phi is still the right eigenfunction, but for this new eigenvalue problem. And similarly, that phi tilde is the left eigenfunction, but again for this new problem. And in this case, we've got a slightly different characterization of the criticality of the system. So if k effective is less than 1, the system is subcritical. If it's equal to 1, it's critical. And if it's greater than 1, it's supercritical. And we can show that k effective is equal to 1 precisely when lambda star for the time-dependent system is equal to 0. And in this case, the eigenfunctions are exactly the same. They match up the left and the right. But for the subcritical case, again, both systems are subcritical at the same time, but the eigenfunctions are not necessarily the same. And same for supercriticality. Both systems are supercritical at the same time, but the eigenfunctions are not necessarily the same. And so how do we study this system from the point of view of the branching process? And what we need to do is look at the growth of the process precisely at the times of branching, precisely at the generations of the process produced by the fission, because this eigenvalue is weighting only the fission operator. And so in place of xt, the branching process that we had before, we now consider a kind of discrete time process, which I'll denote curly x of n. And this is, again, we put a Dirac mass down at each of the particle configurations and add them all up. But now, rather than looking at a time t, we look at a time n, where n represents the generation of the process. So we look at all the particles that are nth in their genealogical line of descent to be the result of a fission process. So for example, all the neutrons that are produced from the first fission event in their genealogy are in generation 1. All of the neutrons that are produced from the second fission event along their genealogies are in generation 2, and so on. And again, we do exactly the same thing. We look at the average of this process under the action of some function g, and we look at its associated evolution equation. And the form of this evolution equation is a bit more compact, because we just say, well, when does the first fission event happen? So we integrate in between 0 and infinity, and we say, okay, it happens at rate sigma f, so I have sigma f e to the minus sigma f, and so on. And then when I have a branching event, the fission operator tells me exactly what to do. So it's a bit more compact. And here, the RS epsilon s process is the sigma s pi s neutron random walk, because this is how the initial particle behaves until the first branching time. So it just scatters according to sigma s and pi s, and then there's a fission event. And with Alex Cox, Andreas, and Denis Villamone, we obtained a pair-Frobenius result for this system. So under the assumptions, so I think this was H1, and I can't remember the other one, but assuming that there's some minimal fission activity, we can show that K star exists, which is our version of K effective. And we have phi and eta, which are the right and left eigenfunctions. Each associated to the eigenvalue K star to the power n, where n is the generation. And again, we have exactly the same convergence to the stationary distribution. So we look at the process, we normalize this time by the growth k to the minus n, or k to the n, and this converges to the stationary distribution. And so what does the many-to-one process look like for this system? Because ideally what we want to do is go through the same processes for the continuous time one and draw parallels from that. So what does the many-to-one look like for this system? So now I'm going to consider a sigma pi random walk, where pi is now given by this combination of the parameters here. And we can think of this process as being built as follows. So we have a neutron random walk. So the particle just moves in a straight line until it scatters. And this time it's scattering with rate sigma instead of alpha. And when it does, we flip a coin. And we denote the random variable ik to be this coin. And if it takes the value 1 with probability sigma f over pi, sigma f over sigma. And its new velocity is then chosen according to a random variable theta f, whose probability density is given by pi f over m. So this is saying that my scattering event came from a fission event, and so I uniformly choose one of the offspring to follow. And on the other hand, the random variable, the coin flip, takes the value 0 with probability sigma s over sigma, and then its new velocity is chosen according to theta s, which has density pi s. So the scattering in this neutron random walk really comes from a scattering in the branching process. And so we can encode the neutron random walk by this combination of the coin flips and the densities, the random variables after the coin flips. And based on this construction, we can define Tn to be the time of the nth scatter of the neutron random walk that came from a fission event. So it's not the nth scatter in general, it's the nth one that came from a fission event, the nth one that caused the coin flip to be equal to 1. And this gives us a many-to-one formula for the generational process. So instead of an exponential factor that we had before, we've got this product function here. And this is saying to compensate for the extra mass that I don't have in my neutron random walk, at each of the scatter events that came from fission events, I'm going to weight it by the mean of the fission density. And again, we can show that this exactly equals the average behavior of the neutron generational process. And so the Perrin-Frobenius result holds for this process as well. And so then we can go through the motions with this process as well. So for future research directions, open questions, open for discussion. One thing, of course, is we just do it all again for discrete time and see what we can say about that. And I'm pretty sure there will be some difficulties that arise that are not straightforward and not directly applicable from the continuous time process. But of course, there are also lots of other open questions. So of course, as the branching process evolves, the environment, the nuclear material does change over time because you're splitting open nuclei, you're changing the composition of the reactor. So how does this affect the process? Can we look at effects of temperature on the system, pressure? What happens when we include the effects of temperature in the cross sections, the effects of time, mass-dependent branching processes, and so on. And there are also lots of other areas of application. So there's not just fissile systems. There are some systems where you just have particles scattering around genuinely with no potential term that are of interest in healthcare and shielding problems, source detector problems. And so you're really interested in rare event simulations. And what can we learn from the probabilistic system here? And also, of course, there's not just nuclear reactors that are of interest. There's lots of other settings where neutron transport and more generally radiation transport are applicable. So thank you very much.
Okay. So, sorry, I'm eating cough sweets here. Do we have any questions? I think, again, as before, perhaps it's on me to start things off. So, tell us again about the level of generality that you think this. Let's take the moments, for example. I mean, how general is general realistically?
Take a Markov process that branches at some bounded branching rate and has bounded mean offspring. Yep. And I think you can deal with very general. Well, you can deal with a very general state space, and you can show that, with non-local branching. So it doesn't even have to be that the particles are produced at the point of branching. They can be scattered all over space according to some weird law, whatever you want. And you can show that the
non-locality here in the neutron setting is a little bit confusing, right?
Yeah.
Because you're not. It's non-local in the
velocity variable.
Velocity, but not in the position.
Yeah, exactly. Yeah, so it's kind of non-local in half the variable, let's say. So you're produced at your new particles are produced at exactly the same spatial position, but their velocities do not have to be the same and they won't be the same as the parent neutron. So that's where the non-locality comes in here. And as I said before, this kind of method that we use also holds for super processes as well.
I can see a hand up. Cecile, do you want to ask a question?
I was wondering at some point, so it was page 22, you said you wanted to do a law of large numbers with respect to the initial population size. Right? Is that
no?
Okay.
I think I mentioned this as like an open question.
It's an open question, so
Possibly.
I was wondering what you meant in terms of the initial population size. Do you mean you want to make the initial population size go to infinity?
Yeah, something like that. Yeah.
At the same time as the time, right? So you look at the process at time t, and you want the population size to grow with t.
Yeah.
Okay.
Yeah.
And
just to look in general at how the initial population size does change things.
And how would you do that?
No
like,
idea.
Okay. Cool. Thank you.
Thanks.
Hi.
Pascal.
Yes. Yes. It's good that you stay with this picture here. So I'm a bit confused about the interpretation, because as far as I understood, so the neutron branching process is a way, so you're actually calculating, you're interested in the Neutron transport equation, and the Neutron branching process by taking expectations allows you to represent solutions to the Newton transport equation. But as far as I understood, the Newton branching process is not meant to be a macroscopic model of what actually happens in the process, right, inside the reactor. So how can you interpret these like, for example, results on clustering or genealogical structure of the Newton branching process in terms of a real microscopic model?
So it would be looking at the spatial distribution of the particles after a certain time. So really looking at where they end up clustering, and they end up moving around in clusters. So it's just following that kind of pattern of particles.
Sure, but as far as I understood, so these particles are not meant to be real neutrons, right? I mean, it's the branching process, as far as I understood, is a way to represent the Newton transport equation numerically, but it's not meant to be a real particle model. Or did I misunderstand something?
So it is well, maybe I don't understand the question, but it is sort of a representation of the real life system. So
in effect, the fission is, if you look at the physical process, it's essentially what a neutron branching process is.
It is supposed to exactly match that behavior.
I mean, I'm referring to the first lecture, right, where the Newton branching process was introduced in a different way. It was not introduced as here is a microscopic model of what happens, but it was introduced as here's the Newton transport equation, and here is a branching process which allows us to represent the equation. But now you're, I mean, the real claim is that it really reproduces what it's really meant to be a physical model.
Yeah, exactly.
If you can answer Andy's question.
Yeah.
So if you can find the answer to Andy's question, which is what is the correct branching law rather than just the mean, right, then yes, it is the actual physical process.
Mm-hmm. Okay. Good, thanks.
And this is a good comment actually for the BBM guys who like their rightmost particles. We've spent a lot of time in the last 20 odd years looking at rightmost particles and clustering around rightmost particles, but nobody's ever really, there's been very, very little work on high dimension and cluster. I mean, this was a surprise to me. Eric showed, these are the very same pictures that Eric showed me. And I had always assumed there was a kind of homogeneous smearing out in space of these branching processes, but no, it doesn't happen that way. And I think we had our eye off the ball, quite frankly. We were too busy in one dimension, and we'd not really looked at this as a community. We'd not really looked at what happens in high dimension. Perhaps the super process people maybe a little bit less surprised at this. I don't know, but
But is it, I mean, it's due to the criticality, right? It's due to the fact that your boundary conditions impose, I mean, you want a system, I mean, that's how I understand it from an outsider perspective, that you actually want criticality because you don't want to create a nuclear bomb, right?
Yeah, I'm not sure actually. I'm not sure I know the difference. I mean, Alex, if you want to say something about that, do chip in. But I mean, the way I understand they run nuclear reactors is that they make them slightly supercritical. They let them kind of grow, then they temper them back down again. So they're constantly trying to drag it back to criticality from a slightly supercritical state. Because of course, if they genuinely put it in the critical state, then as a result, Emma showed that we all know that it will play out with probability 1. So I don't know is the answer. I honestly don't know the answer to that. I just don't know enough about spatial. This is, I guess, what I'm saying. Alex, do you want to?
I mean, I had a question, but I mean, I think, and again, I'm probably not the expert in this room, but if I understand the way they operate the reactors, you have a control rod which you can basically lift up and down, which will slightly, which depending on how you lift it up and down, will slightly raise or lower the criticality. So if you think it's starting to go, I mean, and I guess you have ways of measuring like temperature. So if it's starting to go slightly hot, you will lower the control rod and you will absorb slightly more neutrons. So you can do this dynamically. One of the things that I hopefully will mention tomorrow, but I can say a bit now, I think is that the timescales that this happens over, I mean, typical branching chains happen over very small timescales, but there are what are called delayed neutrons. So, and I think Emma hasn't particularly mentioned this today because there's lots of other stuff, but some particles will collide with a neutron, and often it doesn't really matter if you're talking about things like criticality. So you collide with, sorry, an atom of uranium or something, part of the fuel rod. And what will happen is the neutron will be absorbed, but it won't decay instantly, and it will decay perhaps over an order of seconds or minutes. So there are particles that haven't really been in Emma's, I mean, I think you can build it into the models probabilistically, and we've done this in some of the papers. But the order of, so as your temperature rises, there are particles which take a sort of a second or two to come back into the system. And that's enough time for your reaction of things like the control rods to sort of monitor the criticality. So you want the system to be close to critical, but the last bit you can control, and there's enough time to do it because of these delayed neutrons. So what you sort of do is you have the system without the delayed neutrons being subcritical, because otherwise you can't control it. But you hope the delayed neutrons will put you back over criticality, or at a point where you are able to control it using some sort of feedback. So I believe that. I mean, yeah, there are other people here who might be able to confirm or not, but that's broadly my understanding.
And so that's not incorporated in the model yet. Did I understand that right?
No, not yet.
Not. I mean, I think if you look at the models Emma had, you can write down variants of the. I mean, I think Emma didn't write down the multi-particle version of this, which we have done as well, and your notation gets heavier and you can account for these delayed neutrons. But typically, if you're talking about something like criticality, you're worried about stationary states, and it doesn't matter if your neutron has been there for 5 minutes before it gets spat out again, because there would have been one 5 minutes ago that was exactly the same. So for a lot of the, so it only matters when you're worried about the time dynamics of the reactor. In the stationary states, it doesn't matter because there was another one that did the same thing 5 minutes ago, and so you get the sort of stationary state without worrying about, is this particle being stuck for 5 minutes or not. And that turns out to be enough to, I mean, if you design these things carefully to get the criticality and so on to work. I hope I haven't said anything too wrong. So I also had a question, if that's okay.
Sure.
Yeah.
Which is possibly for Eric. Clustering you've got in this picture, is that because you are doing some sort of population control, or so killing off particles to keep a constant number?
I have a feeling this was from the branching process, but Eric can probably correct me if I'm.
Yes, that's right. It's without population control, you have exactly the same kind of clustering effect going on. I'll discuss that in my talk this afternoon.
Okay, is this a critical case?
Yeah, it's in the critical case, but you have papers from the 1980 where people have a look at the spatial correlations also for supercritical cases.
Okay.
So the overall number of neutrons is diverging, but you have more or less the same spatial correlations appearing in the population.
Is that the paper of Cox and Griffith?
No, it's a paper that I can put in. I can put it in the thread, but it's a little bit later from a Russian guy. But
Okay.
I'm sorry, I forgot its name.
Okay,
his
no,
name.
that'd be great. No, that'd be cool. Thank you. Any more, Alex? In that, hand down. Okay. Just one thing I want to add to all of this. I mean, there's been a strong focus on nuclear reactor cores here, but this story that Emma's saying is not restricted to nuclear reactor cores. The transport equation you see it's an example of the Boltzmann transport equation, and it's a specific example of Boltzmann transport equation. And essentially all radiation, all within moderation, there are certain types that it doesn't work for, but lots of radiation can be written down as following these transport type equations. So proton beam therapy, for example, the way in which protons kind of pass through the body, the interactions they have. In that case, you need to add the effective energy loss when the protons interact with atoms. In multi-species, as we call it multi-type in branching process, but it's more like multi-species. So, modeling gamma rays coming off neutron interactions as well. So gammas have a slightly different behavior, but they all fundamentally can fit this neutron transport equation or variant of that. I mean, I'm talking at the moment to a guy in NASA who's interested in cosmic radiation. And one of the problems with designing spaceships, spacesuits, that kind of thing, is when the cosmic ray comes in, hits material, it interacts with the atoms in the material and sprays out a whole load of other subatomic particles, which actually the more dangerous in some sense to the human body. But again, they use the transport equation to model this. So although the branching process has a very nice feel in the context of the fission that goes on in a nuclear reactor core, I mean, there are still many physical representations you can put behind transport equations that describe other particle systems. And I think I had a sneaky peek at Tony Leliere's talk, and I think he's even going to look at neutrons kind of going around corners, escaping in complex, in corridors and stuff like this. And so it's not just about reactor cores. There are many scenarios, and we've heard also about startup burn-in. Does the source term matter? Is the source term dominant? Is the source term not dominant? In huge variety of scenarios where one can pose questions that I think pertain very much to our knowledge on Markov processes and on knowledge on branching particle systems correlations within that and so on and so forth that we just have not put our attention to at all.